Hello and welcome back to Rotary Rockets. Today we're going to be taking a look at the development of a new PVC casing rocket motor. Now this is the replacement for our original SuperMonkey motor that we abandoned a while back. So if this model works, this will be our new SuperMonkey motor. So for those of you who have been following our channel, you know that we've developed some PVC motors in the past, and we eventually abandoned that and switched to a full metal casing, which is our RoboMonkey motor. And that's an aluminum and steel combination casing that's fully reusable. Now that motor works really well, but it is a little bit on the heavy side. And you might be thinking, well, why are you going back to PVC since it's clearly not nearly as strong, and it does have a problem of tending to blow up a lot if you overpressurize it. So the reason is we found some new ideas on how to do the nozzle assembly. Now this is one of the very last SuperMonkey motors that we used, and it worked very, very well. But what we were getting was some intermittent failures in the nozzle area as far as nozzle retention or nozzle blow-by. On this particular one, I've cut off the threaded end here, but this blew out right here at this point just between the nozzle and the PVC piece. So let me show you a couple things about that particular motor and why it tends to fail, and what we've changed on this new model. So for this particular one, we had a male threaded end on the end of the rocket motor. And then the nozzle assembly had a female thread that threaded onto that. And they threaded on very nicely and seated very good. We put some Teflon tape around those threads to help keep those threads locked in and sealed up very well. But the problem is, if you slide in the PVC motor casing here, what you have is about 1 inch inside there of PVC that is now fully exposed to the gases as they're trying to approach the nozzle assembly. And that area that's exposed is the inside of that entire threaded assembly. And it's not very strong, it's only a thin wall area there, and that's exactly why we had that blowout, which was just at that point between the end of the threads and where the nozzle assembly mounted on. So to have a section of PVC exposed to those gases inside is really not acceptable at that point, especially at the bottom of the motor. So another option that we had tried was very similar. Instead of having a male fitting at the end, we had used a female fitting which has female threads on the inside. And then doing different types of nozzle assemblies that fit in there. Now the problem that we were seeing there, again, was very similar as far as blow-by or melting. If you take any kind of pipe nipple or pipe fitting, this is just a sleeve assembly just as an example. You thread it into that, it binds up very early on. You see it won't seat in. Now on the inside, what that means is that you have an area of about half of the threads in there that are not protected from the gases of the motor, because the fitting just simply doesn't go all the way up into those threads. And it doesn't matter whether you use a metal fitting here or a PVC fitting or any kind of fitting. It's just the nature of this, because of the tapered fitting for these plumbing fittings, it just doesn't go down all the way into those threads. So again, if we did that, we would have exposed area of PVC inside there. So what changed that allows us to do this newer style, or at least try this newer style? And the key is this piece right here. So this is, even though it's a bigger size, we're going with 1.5 inches as opposed to the 1.25 inches, but it's the same fitting basically. We have a slip coupling at the top and we have female threads at the bottom. The difference is this is regular plumbing PVC, This is gray PVC. Now here in the United States, the gray PVC is used for electrical conduit, but it's still PVC. There is something interesting different about the threads on these though. So this is just a piece of a pipe nipple. I had bought a pipe nipple and cut it in half. So when you thread that in, the interesting thing is on this type of fitting, it doesn't stop. It just keeps going all the way, and I don't know if you can see it on the inside here, but it does bottom out all the way in, all the way through the threads, and makes contact with that little ring that's on the inside there as a stop between the slip coupling and the threaded coupling. That's the reason that we're going back to the PVC, because I think that with that change, we can make this work. So our intended design for this is to take a nozzle assembly. This is just an example. We'll actually make a one-piece convergent divergent nozzle, but just as an example, we'll have this threaded piece of the nipple that threads into there with the pipe tape around the threads to keep the blow-by from occurring. And then a nozzle assembly will simply be welded into that so that you have the convergent starting right here at the top and then the divergent coming out the bottom. And that will be the finished nozzle assembly. But because we really don't know the capabilities of this casing as far as pressure, we are going to actually make some test nozzles. So what I've got here is just some 1/8" steel, cut out some little rings, and we'll make some different size nozzle openings in the center. Those fit down nicely into that fitting, and then this will just go in and hold that in place. Now this particular one is the first one we're going to start with. It's a number 24 nozzle, which is 24/64 of an inch or 3/8 of an inch. So that's going to be our first one. We're going to keep reducing that nozzle size until we actually get a failure, whether it be some type of a blow-by issue or an actual explosion. Then what we'll do is simply move up to the next nozzle size above that we tested successfully and continue testing with that. Now the fuel cell that's going to go in here is a little different than what we normally would do. Now this is an 1.5" inside diameter PVC by 9 inches long. That's going to be the casing and the entire fuel cell. We're going to actually cast the fuel right in that assembly with the paper liner in there and everything, and then just assemble everything all together. So it's going to be an 1.5" outside diameter for the fuel cell. We'll have a 1/2 inch core hole down the center of that, total of 9 inches long. Now normally with a motor of this style you would have probably 3 individual fuel cells in there. Instead we're going with the one single fuel cell. The reason we're doing that is because when you have multiple cells and they're burning, you end up with a hot spot in between those cells, especially because we don't have any kind of a protective liner. Now we are going to have the paper liner that goes around the fuel cell, but that's not really very fireproof or heat proof. It burns off very quickly. So you end up getting these hot spots in between the cells. Now we did have multiple cells in the original SuperMonkey, and you could see those hot spots during our ground tests. It didn't seem to be enough to cause a problem, but this is a larger diameter, and we really don't want to have an issue where we burn through the casing or cause some excessive heat in the casing in those areas that could cause it to blow. So that's why we're going with the single fuel cell. Here I've got the first fuel cell that we cast. We cast the fuel directly in the 9-inch piece of PVC that is the motor housing. Now on the end cap, I did put in some rockite anchoring cement into the bottom of that and let that set up. It's nice and flat in there. What we found on some of our other larger PVC motors is that if you don't protect that cap from the heat from the center of the motor or the core section is just going to blow right through the top, and you'll have a catastrophic failure at the top of the motor. So that's a heat shield for inside there. We'll go ahead and use the PVC glue and glue that onto that end. And then here I've got one of our finished washers here. This is a number 24 orifice hole, or 24/64 of an inch. That just goes into the PVC piece, and we'll put some thread tape on here and tighten that on, and then that will get glued onto the other end, and that's the finished product. Now, there is one area where I see for a potential failure here, other than the fact that the whole thing may just explode, and actually that's not a bad thing, because we are going to be testing this until it does explode or has some type of catastrophic failure. That's how we're going to figure out what the best nozzle size is. But because this washer is really just sandwiched in between this retaining piece and a little lip of PVC in here, and that lip of PVC is actually exposed to the gases inside here. Now, it's kind of a thick wall section because of the way that the fitting is made, but it is still exposed. And that's holding the other side of this washer. So we're sandwiched between plastic, the washer, and then the retaining ring. There is the possibility that in the 1 to 1.5 seconds of the burn time, that this washer may melt the PVC ring and either move sideways or just get tipped or just displaced in some way, and we get gases that will come around this washer and come out around the perimeter of the inside of this ring. So we'll be watching for that on the video, although I'm not really sure if that does occur, if we're going to be able to see the results of that. So it is something we'll be watching for. But I didn't really want to take the time and the expense of welding this washer to the retaining ring here each time, because this is really just a one-time test, and I didn't really want to keep buying and cutting these threaded pieces here each time. So hopefully that holds together long enough for us to do the test. Now, we are going to be putting this entire motor onto our thrust test stand when we test it. Now, I do realize that when you use just a washer like this for the orifice, it's not very efficient as far as putting out maximum thrust for the motor, because you don't have a convergent side and you don't have a divergent side. Now, the finished product will have a fully constructed convergent and divergent nozzle assembly, but the test ones don't. So the test results that we get as far as thrust are not really going to be accurate as far as what we're capable of achieving with the motor. But what we want to see is if we use a number 24 and then we end up going to a 22, or we end up going to a number 26 nozzle, we just want to see the differences between those different thrusts to see if one gives us more or one gives us less. So we will be charting the thrust off of this as long as this motor holds up, and we'll see what we get out of it and compare that to some other tests a little bit later. So we're ready to put this together, and then we'll head out to the test site and we'll see what we get for results. Alright, so this is ground test for our first new design RoboMonkey with a number 24 nozzle. Well, we always knew there was the possibility that motor would explode, and it did. So that's not the worst thing in the world, it's just part of the testing process. But what was most disappointing, I think, was the amount of time that it actually was able to survive the pressures. It was burning for about 2 video frames, which is about 1/15 of a second before it exploded. Now, the prediction would be that a motor with a fuel cell of this size should burn for about 1 to 1.25 seconds. So with only that fraction of a time, we weren't even close to the maximum pressures that this was going to build up. So definitely way off with that nozzle size. Let me show you those video frames. So here's video frame 1 where the motor seems to be fully ignited, and then the second frame, and then the third frame is boom. The blast radius for this was about 50 feet in all directions. We went around and picked up every little bit of plastic that we could find. It doesn't even look like this is enough plastic to reconstruct the tube. I think some of it just got blown into tiny smithereens that we could never find. The retaining ring and the nozzle washer held up just fine, so we'll just clean those off. We'll be able to reuse those. The end cap, which was double wall thickness here, held up pretty good, although it clearly got blown off, but physically it held up good. There's a little damage to the rockite at the end there, but it doesn't look like it's burn damage. I think it just got cracked from the blast. And then all the rest of the bits. So we're going to stick to our original plan, and we're going to jump from a 24 nozzle hole to a 26 nozzle hole. So I'll just drill this out to 26/64 of an inch. That will put us at the same diameter as what we were using for our original SuperMonkey motor before we abandoned that. So that should be interesting because it'll bring us back to that same size. And that motor was not exploding, but we do have a different configuration of fuel cell in this, so that's going to change the burn rate and the pressures. So it'll be interesting to see how that holds up. So we're going to go ahead and reconstruct a new one out of some new parts, and we'll give that one a test with a number 26 nozzle. Wow, that was great. Now, we obviously blew the nozzle out, but the casing didn't explode. So that tells us that we're really close to where we need to be for that nozzle size. So let's take a look at what actually happened here as far as why the nozzle blew out. So with this temporary nozzle system, there really is no heat dissipation. So this is going to get really hot really fast, which just turns those threads in there to mush, and the nozzle just gets blown out because the gooey threads just can't hold that in anymore. So that's really simple. The new nozzle that we're going to build with the convergent and the divergent is going to have a lot more steel content. So that will absorb and dissipate the heat a lot faster. So this problem of the nozzle coming out due to the heat during the burn, we're really hoping that just having the proper nozzle on there with more mass will help that not to happen. Now the scale was showing 75 pounds of force when the nozzle finally did blow out, which is really good, but I do expect to see an increase in that force when we get a proper convergent and divergent nozzle. So that'll be really interesting to see the difference between this test nozzle and a proper nozzle. I do want to show you something really interesting that happened to this orifice washer during the burn. So I'll bring this washer up close, and you can see that it has a little bit of a curve to it. Also, it has this little lip of steel sticking up beside the hole. So there was enough heat and enough pressure in there to bend that 1/8 inch piece of steel and also bend a little piece of the hot steel away from the orifice hole and form that lip. So I'm going to go ahead and build that finished nozzle assembly, and in the next video we're going to assemble a new motor with a complete nozzle and do a ground test on that. So if you like what we're doing here, go ahead and click that like button. It really helps our channel out. We've got a couple things in the works. We're developing a couple of different motors and also building a new rocket in preparation for one of our new large motors. So go ahead and click the subscribe button as well if you're not already a subscriber, and get notifications for our new videos that we've got coming out soon. And thanks for watching. We'll see you next time.